I hope you had a good coffee break. So we are starting the last session for today, and we will start by a topical seminar by Tyler Corbett, who is a postdoc at the Niels Bohr Institute about effective field theories and neutrinos. And as usual, if you have questions, don't be shy, write something in the chat or just open your mic and ask your question. Okay, so Maurizio has started the recording. Tyler, please, the floor is yours.
Okay, great. So I'm an effective field theory person. I'm mostly a collider physics person, so I'm not an expert in neutrinos, but this was a fun review for me, and it's a way to share some of the effective field theory stuff I work with you guys. So please interrupt me if you have questions. If they're more on the technicalities of neutrinos, I might not be able to answer, but all the effective field theory related things I should have an answer for. Did it go to the next slide? There we go. So I'm going to start with a basic example of an effective field theory. Then I'm almost entirely going to talk about neutrino mass models and effective field theories. Then if there's time at the end, I'll talk about a modern interpretation of quantum field theories in the context of effective field theories. So to start with, prior to the standard model, we didn't understand neutron decay or beta decay, where a nucleus is converted to some other nucleus and emits an electron and the hypothetical neutrino. So in a very non-historically accurate manner, I can describe Fermi's solution as, he says, let's take the field content in the symmetries of the model we do know, which in the day was quantum electrodynamics, and we're going to form an operator that could explain neutron decay. So that field content is the photon and the fermions and the U1 symmetry of QED. You write down some operator here, which connects a neutron, a proton, a neutrino, and an electron, and you just put some coupling out front. And this term in the Lagrangian gives a 4 fermion interaction that could describe neutron decay. And to keep the action unitless, this GF needs to have units of 1 over some mass quantity squared. Nowadays, we know in the standard model, we can describe neutron decay, or in this case, I do muon decay, so that you don't have to deal with composite particles. We know that this unfolds simply through the exchange of a W boson. So muon decays to 2 neutrinos and electron via a W boson. The Lagrangian from the standard model that describes this is 2 fermionic currents. They couple to the W's, and you couple those 2 fermion currents via a W propagator. And you get an amplitude that looks something like this. Now, the mass scale of this problem is the muon mass scale, which is 100 MeV. The mass of the W is 80 GeV. So this really actually looks like 1 over the mass of the W squared, because this K squared is essentially 0. So instead, it looks exactly like Fermi's contact interaction. It looks like these 2 fermionic currents are put together with a 1 over m squared interaction. So this effective operator gives me an amplitude that looks something like this, whereas the full theory gives me an amplitude that looks something like this. This effective operator is what I'm going to refer to as an effective field theory. And I'll flesh this out a little bit more. And throughout this talk, I'll just talk about, oh, here's some model's prediction. Here's the effective field theory's prediction. The matching between these 2 works, so that's an effective field theory. There's a lot more formalism that goes into this that you can study, and I've got some references at the end of the talk if you want to dig into that. But for the purpose of this talk, I'm going to stay very simple, derive an amplitude, say that the effective operator's amplitude looks like this, so they're the same theory. Now, if this isn't good enough, if Fermi is not good enough and I want to be more accurate, I can go to the next order in this expansion. That's the next order in the effective operator expansion. It's got a 1 over m to the 4th suppression instead of 1 over m squared. It's got these 2 derivatives that pick up the k squared over m squared dependence. And I can keep doing this. So this effective field theory is also systematically improvable. So this motivates the idea of what an effective field theory is. There's one major underlying assumption for an effective field theory. That's that the new physics scale is much larger than the energy scale of the experiments, the measurements, whatever we're doing. And from Fermi's perspective, what we call that a bottom-up effective field theory. We start with what we already know. In the case of the example I gave, QED, modern examples are the standard model. We use the symmetries of that model and we build a bunch of operators that have mass dimension greater than or equal to 4. We truncate when it's appropriate in the 1 over the mass expansion. And then we can constrain these operators in experiment and try to infer properties of new physics at a scale we can't even see in our colliders, not directly. Alternatively, you've got the top-down EFT. I know the standard model. If I take these W bosons and I integrate them out, what I did in the last slide, I get the Fermi theory back. So in this case, I start with my favorite model in mind, which could be Seesaw, SUSY, the standard model. I integrate out these heavy degrees of freedom, which for my example was just matching, but there's a lot of formalism that goes into what it means to integrate out heavy degrees of freedom. And you derive model-dependent relationships between these new operators. And these new operators are only in terms of the known degrees of freedom of your model. So with all of this said, we can form what's called the standard model effective field theory. This is the effective field theory we use to study new physics that's at a mass scale much larger than the electroweak scale, which I denote by the vacuum expectation value of the standard model. There's alternatives to this, but this is what I'll focus on. Basically, we've got a bunch of new operators at any given dimension. This coefficient C is called a Wilson coefficient. You sum over these and you try to study your low energy physics and constrain new physics. This standard model EFT is really a Taylor series in either the electroweak scale over the heavy mass scale or the energy of your process over the heavy mass scale. And as long as these quantities stay much less than 1, you have a well-defined quantum field theory. These dimension 6 terms that are here are more collider phenol relevant. But this dimension 5 term is the leading term in the standard model EFT. And it's called the Weinberg operator typically, and it actually gives you neutrino masses. So this is what I'm going to focus on for most of this talk. So if I take this, I expand around the Higgs doublet and the lepton doublets, I get a mass term, a Majorana mass term for these neutrinos. So it's really exciting that the leading operator in the standard model EFT, so the least suppressed operator, is a neutrino mass operator. Unfortunately, we know that the Seesaw scale is really high. So that doesn't necessarily, it's not as exciting as it seems when you first learn about this operator. So Weinberg wrote down this operator back in the day. He was studying baryon number violations, said, oh, by the way, there's a leading operator that actually gives neutrino masses. So I take this operator, I expand the Higgs doublet in terms of the goldstones and the Higgs in the BeV, expand the leptonic doublet in terms of the neutrinos and the charged leptons, and I get something that looks like this. This V squared term is exactly a Majorana neutrino mass. This H term couples the Higgs to neutrinos. And so you can see here, I've written a little diagram. This is the mass of the neutrino, or the mixing due to the mass between 2 neutrino flavors. And you see that the Higgs coupling to 2 neutrinos is the mass of the neutrino divided by the vacuum expectation value. This is exactly the form that you get out of the standard model for the coupling to any other fermions. So this makes a lot of sense when we're thinking from a standard model perspective. So previously I talked about bottom-up theory. Fermi writes down an operator that we now know is the W boson, or a reflection of the W boson at lower mass scales. And then from the top-down perspective, we can say, I know the standard model, I can integrate out these W bosons and get the Fermi theory. So now what I want to talk about is how can we get Weinberg's operator from some sort of UV model. And the most obvious first thing to try is type 1 seesaw. So we introduce some heavy right-handed Majorana neutrino. You've got a kinetic term in the Lagrangian here, and you've got a Yukawa interaction between the leptonic doublet, the Higgs, and the right-handed neutrino. This gives rise to this diagram, which couples two Higgs doublets to two leptonic doublets. You've got a mass insertion here, and you've got the Yukawa coupling here. I write down this diagram, I do the calculation, and I obtain this amplitude. So I've got the two Yukawa couplings. I've got an on-shell spinner here, an on-shell spinner here, and then I've got the propagator for a massive fermionic field. If I take this and I Taylor expand it in 1 over the heavy mass scale, I get this term, plus some corrections that go as the momentum divided by the mass squared. Now, if I take the Weinberg operator and I do the same calculation, or I calculate the amplitude between two Higgs doublets and two leptonic doublets, I get this same amplitude, but with this Wilson coefficient and the 1 over lambda. So matching between these two, I see that this theory actually corresponds to, as long as the heavy right-handed neutrino is heavy enough, this Weinberg operator. This is the prediction for the Wilson coefficient, and therefore also for the mass matrix. And you've got this suppression scale that is the heavy right-handed neutrino scale. So instead of studying type 1 seesaw, I can study the effective field theory with just this operator. Or I can add corrections coming from this, which gives me more operators. Now, I can also look at type 2 seesaw, where I introduce a heavy triplet scalar, and I'm going to burn through this a little bit quickly compared to the last slide to try to get to my last slides in this talk. So I've got an interaction between the two Higgs doublets and this triplet. I've got a Yukawa interaction between the two leptonic doublets and the triplet. This one has mass dimension, and I get another diagram. This diagram, again, couples two Higgs doublets to two leptonic doublets. There's the exchange of the heavy field. If I do the expansion in the heavy mass scale, I get this massive coupling G over m squared, which is a 1 over m mass suppression, with a prediction of the mass matrix to be this Yukawa coupling, and the heavy mass scale being the mass of the delta squared over this massive gauge coupling. Not gauge coupling, but massive coupling. So again, I get the Weinberg operator. And then I can go to the other seesaw, type 3 seesaw, heavy triplet fermion. I've got another Yukawa coupling. It's the exact same diagram from the type 1 seesaw. And again, I can do this expansion in 1 over m. And again, I get the Weinberg operator. Here's the prediction for the mass matrix, and here's the suppression scale. So this is really interesting.
And there was a question in the chat.
Okay.
I'll briefly interrupt you. So it's actually connecting back to, I think, your introduction. So it's a question by Jamie. Can these new effective field terms break some symmetries of the top theory? What are some consequences if this is possible?
Of which theory?
So it's top in quotation. So I think this is basically the up theory. So if you have like the top down or bottom up, so the underlying UV completion. So the question is if these effective, I mean, if I understand the question correctly, Jamie, if these effective field terms can break symmetries in the underlying UV theory.
If I'm going bottom up, then I will not see the reflection of the UV completion in my effective field theory. When I start constraining it from experiment, nature is going to tell me what those correlations are that are reflections of the symmetry of the UV theory. If I start from a UV theory and I integrate out those heavy degrees of freedom, the relationship between my Wilson coefficients and the operators that come out of doing that procedure will reflect those symmetries. So I hope that's the answer to the question.
Thank you. Yeah, I think that's it. Thanks.
Okay, great. So now we've looked at 3 different seesaw mechanisms for getting neutrino masses. They all gave the same leading operator. So this is really interesting, at least to me, because it means I can study one theory, the effective field theory, and be studying all these different UV completions all at once. I don't need to study 32 different models and constrain all of them, doing all of my phenomenology of whatever I'm studying, and study each one separately. I can study one model and constrain all of these. And the only really important implicit assumptions here are that the new particles are much heavier than the standard model particle content, or really than the electroweak scale and the mass of the top, which is the electroweak scale. I assume the standard model gauge symmetries in fields, and this is really well justified from precision measurements, except maybe the Higgs doublet can be relaxed, and that's another type of effective field theory, not the standard model effective field theory, but I'm not going to discuss that here because I don't have nearly enough time. And then we assume that the doublet field, that our effective field theory is written in terms of these doublets, L and H and whatever else from the standard model, instead of their components. And this were really the only assumptions that went into this. So now I have a much simpler theory to study, or I have only one theory to study, as long as I assume that the new physics is very heavy. And if I go from what we talked about in the last few slides, these seesaws, and I say that the mass scale of the neutrinos is 0.05 eV, I think that's some sort of atmospheric constraint. I got it from the review that I mentioned at the title slide. This gives me the vacuum expectation value squared over the seesaw scale. If I solve for the seesaw scale, that gives me something like 10 to the 15 GeV. And one of the biggest problems with being a particle physicist right now is that all the nice new physics models seem to predict energy scales that are enormous. And SUSY seems not to be at the electroweak scale. So the seesaw scale is way too high. I don't like this. And I want to study something that still works in the effective field theory context, but brings down the energy scale a bit. So maybe I see the new physics in my lifetime at a future experiment. So let's take this model from this archive paper. Introduce a fermionic quintuplet, a scalar quadruplet, and here's the Lagrangian. You've got kinetic terms, and then you've got some Yukawa coupling between the leptonic doublet and the new scalar and the new fermion, and you've got some sort of interaction in the scalar potential. Now I can write this diagram. This is the leading diagram that'll match onto the effective field theory. I've got two leptonic doublets. And instead of being a Higgs here and here, like in the case of the seesaws that I showed before, type 1 and type 3, I've actually got the heavy scalar here connecting 3 and 3 more Higgs doublets. So instead, my amplitude looks something like the Yukawas, this lambda squared, which is the scalar interaction. I've got one fermionic propagator, which gives me the p slash over p squared minus m squared. And I've got two bosonic ones, which give me an extra p squared minus m squared squared. If I expand this, instead of like in the type 1 through 3 seesaws, 1 over m dependence, I get 1 over m to the 5th dependence here. And the next correction is p squared over m to the 7th. Actually, it's probably p over m to the 6th. That's probably a mistake. This matches on to, instead of the Weinberg operator, a whole new operator. It looks like the Weinberg operator multiplied by h dagger h squared. So instead of Wilson coefficient over lambda to the 1, I've got Wilson coefficient over lambda to the 5th. The mass matrix prediction looks like this, and the heavy mass scale is the scale of the sigma and the phi, which I've taken to be the same. And if I do the same procedure that I did in the last slide and set the neutrino mass scale to 0.05 eV, I get Vev to the 6th over lambda to the 5th. Solving for lambda, I instead get order 100 TeV. So instead of 10 to the 15 GeV, I'm now down to a more reasonable mass scale. Still not something we'll see in a collider experiment in our lifetimes, but something more reasonable. Now there's another way to do this as well. Instead of making this type of model and having some tree level contribution, I can also do loops. Now I didn't have the time to go and look at an explicit model to give you here, so let's just take a particular topology. It connects two Higgs doublets and two leptons, and I've got some sort of loop. These are all heavy particles. That's the assumption here. In this case, I have a 1 over 16 pi squared suppression that comes from the loop. The vacuum expectation value squared over lambda, that's just the Weinberg operator again. And this gives me a heavy mass scale of maybe 10 to the 12 GeV instead. So these are two different ways that I can bring that heavy mass scale down, but I'm still in an effective field theory. So instead, what I can do is I can look at a bunch of different ways. I can combine these two ways, invent some really convoluted model with NL loops and with twice NH2 minus 1 suppressions by V over lambda. And solving this for the heavy mass scale tells me that at a future collider, maybe I could see a model that generates a Weinberg-like operator at no loops and 5 insertions of H squared, or 1 loop and 4 insertions, 2 loops and 3 insertions, 3 loops and 2 insertions of H squared, or 4 loops and 2 insertions. These are obviously very convoluted models, but these are ways from a theoretical perspective to design a model that gives you the properties you want, like actually seeing new physics in your lifetime within the effective field theories.
Tyler, can I ask another question?
Absolutely.
This was also posted on the Zoom chat here by Shiva. Could you infer any information about the symmetries of the theory at high energy scale, or is it integrated out in effective field theories? I guess the question is, can you somehow see symmetries at very high scales from, properties of the effective field theory?
Yeah, so let's take the example of the Fermi theory again. Now, Fermi just said, let's write down this 4 fermion operator, and it should describe neutron decay. In fact, he just wrote down a vector current, I believe. And then Li and Yang came along and they said, well, there's no symmetry here that actually forbids introducing axial currents. And suddenly you have CP violation. And in fact, if you go and you constrain this Fermi operator and you write it down in terms of all the different possible chiral representations, you find that it's exactly this V minus A form that you get from the standard model from the W boson interactions. So in fact, you are seeing that UV symmetry, that is that the W bosons coupled to left-handed fields, you're seeing that reflected in the low energy effective field theory. So you can experimentally obtain these constraints, these symmetries, and then you can say, I'm seeing these symmetries, how do I UV complete this model? How do I start from the bottom, this EFT, and I find these symmetries from experimental constraints? What UV complete model, what new physics model gives me these symmetries? So yeah, you very much can see the symmetries. Is that the answer? Okay, great.
I hope it is.
So then to summarize what I've talked about so far, effective field theories are mostly model independent. You need this heavy mass scale and you have some assumptions about your low energy field content and their symmetries. For example, I put everything in the standard model, doublets, the field representations, and have the standard model gauge symmetries. You have simpler low energy dynamics, typically, more or less. It depends on what order in the effective field theory you want to keep and what assumptions you're making. But I don't have to study a ton of different models to do the same thing. And this concept that I presented in the last slide here, where I invent some loop order and some operator order, this is called opening up the operators, or it's what some people have started calling it. I can use this to motivate UV models that have the properties that I want. So it's an interesting theoretical inspiration for studying new models of neutrino mass generation. Some important things that I haven't discussed so far are effective field theories also allow us to deal with non-perturbative physics. If strong dynamics generated neutrino masses, it would look to us, working from a perturbative Lagrangian point of view, like the Weinberg operator or some similar operator. And the theory that I can use to actually describe the scattering of pions, kaons, protons, and neutrons is an effective field theory. And you can do this, and you can do these calculations accurately, and systematically and provably, without having to understand how QCD condenses into these particles. And this is called chiral perturbation theory. If I want light right-handed neutrinos for my effective field theory, I can just introduce them and tack them onto the operators, still following standard model symmetries, but forming operators that also have standard model singlet right-handed neutrinos. And then, with the very little bit of time that I think I have left, I just want to mention the modern view of quantum field theories is really that they're a tower of effective field theories. And what I mean by this is, if I have some beyond the standard model theory with some heavy new particles, and then all the standard model particle content, I can integrate out these heavy new particles, and I get the standard model plus the standard model EFT. So the standard model Lagrangian plus a tower of new effective operators suppressed by a mass scale. And the only particles in this theory are the standard model particles in their gauge representations. And then I say, okay, I'm doing physics below the scale of the top quark, of the W, of the Higgs. Now I'm going to integrate those out. And then I come down to below the electroweak scale. And now I've got what's called the low energy effective field theory. And I've got something that looks like a QED Lagrangian, a QCD Lagrangian, and a bunch of effective operators suppressed by the electroweak scale to some power. And I've got 2 uplight quarks, 3 downlight quarks, 3 charged leptons, 3 neutrinos, a photon, and the gluons running around in this theory. And then I can come down yet another step, and I've got basically QED plus a tower of operators related to how QCD condenses. And I've only got photons, charged leptons, the pions, proton, and neutron running around. And you could technically keep integrating these particles out other than the stable particles in your theory. And this is sort of the modern view of how quantum field theories are put together. And really it says the standard model is not the model. It is an effective field theory. And at some higher energy scale, we have a new particle and a new Lagrangian. And above that, we might have a beyond the standard model theory. And this would then have effective operators tacked on that reflect that. And if I want to add in right-handed neutrinos down here, they just get tacked on the way up. And my effective operators just have right-handed neutrinos in them, or other light degrees of freedom that might exist that we haven't observed yet. And I think one of the most important things about this perspective is that top-down implies correlation between operators in the low energy theory. And since we believe in the standard model, at least most of us do, above electroweak symmetry breaking, for example, we have an interaction between leptons that's given by this gauge interaction term, this gauge kinetic term. And above electroweak symmetry breaking, it looks like this. You've got B fields and W fields. Below electroweak symmetry breaking, I expand in terms of the VEV and the components of these. And it implies, for example, the interaction between the Z boson and neutrinos and electrons. It implies there's a correlation between these interactions. And that's reflected when I integrate out formally the Z boson, or integrate out new physics and go to the standard model and go below electroweak symmetry breaking. These correlations are implied. So to put Mauricio on the spot, there's an example from one of his papers where they write down an interaction between neutrinos and a new scalar. Now, UV completing this theory requires that we rewrite the interaction in terms of the leptonic doublet, at least if you believe in the standard model gauge representations. This implies that there's also charge interactions with the phi fields. And technically, you're more likely to get more stringent constraints from those charged interactions because it's very easy to see charged particles. So really, UV completing this theory requires that either I put the particles into the standard model representations, and there's some charged interactions that'll give me more stringent constraints, or I assume the standard model is wrong. Or to put it in more realistic terms, these searches not only look for the new physics that you're presenting when you study these interactions, but they're also really important tests of the standard model and its symmetries and its gauge representations. Because if you were to see these interactions, you would be able to compare them to the charged interaction constraints and try to infer, is there something that's breaking what I assume from the standard model? What kind of new physics is here? And it's a really important test of the standard model. But it's something to keep in mind when you study these sort of interactions. So that's it. I've put together a list of references from that are the best ways to sort of approach these things if you're interested in learning more.
Great.
So,
thank you very much, Tyler, for this great overview. I see there's another question by Shashank on the chat. Shashank, do you want to ask yourself? I can also read it out. So can effective field theories allow us to deal with non-perturbative physics with non-trivial topological effects? For example, sphalerons, instantons, solitons. And he's referring to slide 15.
Okay, just because that's where they're not. Yeah, that's a really, really hard question. My gut answer is no. My gut answer is no, because essentially when you're doing this, you're making an assumption not only about the momentum of the particles and the mass scale of the new physics, but you're also making some sort of assumption that the field configurations, if you will, aren't large. And for me, that means that doing non-perturbative physics like that is very dangerous, because I don't know when I'm doing solitons and these things, what the field really looks like. I'm used to perturbative physics. I'm used to saying this is the excitation of the field. This particle has such and such momenta. So I personally don't think that we should be doing that. Maybe someone else has a better explanation for why it would be safe. But with my understanding, I would say it's unsafe. And this also goes for people that want to study, for example, phase transitions using effective field theories. I think that's also a very questionable thing to do, because there's these built-in assumptions about the field configurations as well. And that, I haven't discussed that, but that's more of a formalism of integrating out the fields topic. So that's something you might run across in, where did I put that? The formalism paper here by Murayama.
Thank you. I see that Nele has her hand up. Do you want to ask your question yourself?
Yes, I would like to. So, hi, thanks a lot for the nice talk. I have a question on these three seesaw mechanisms that you were talking about, because as far as I understand, you say that it's super nice that they all reduce to the same stuff. And my question would be, so this is only leading order, right? So what if then you do this calculation and you want to get back to the individual ones and want to have like higher order calculations? Is this difficult, or would this be easy to do?
Technically, it's very straightforward. The problem is here, when I write down this cute slide, the leading operator, there's only one leading operator. Here in L6, okay, there's one, and then you've got a 3x3 matrix out front. So there's one, or there's 18, because it's a complex matrix. At dimension 6, there's 59 operators. But if you include flavor, it's 2,499 parameters. So it very quickly becomes complicated. The nice thing is, when you work from a weakly interacting theory, like these examples, you don't actually produce all 59 of those operators. You produce a small subset. And then if you loop improve your matching, then you start to generate a lot more. So technically, no, it's not hard. We understand well how to do the tree level matching, and people are developing, in fact, the full one loop matching as an automated tool as well. So it's very much practical. but it becomes much more difficult order by order. But since this theory, since this interaction violates lepton number, you might not even generate any dimension 6 operators. You might only generate dimension 7. And because of the lepton and baryon number violating nature of odd dimension operators, there's actually a lot less dimension 7 operators than there are dimension 6. So that's a very long answer to say, technically it's very straightforward, but there's a lot of caveats. But lepton number violation also simplifies things.
Okay, thanks a lot.
Are there more questions? I don't see any. Then thank you very much, Tyler, for this nice overview. Yeah. We also have a discussion session in half an hour. Maybe you have the time also to join us then.
Yeah, I'll stick around.
Thanks a lot.